All right, welcome back. Make sure you get your notebooks out and ready to take some notes. We're going to talk about heat flow, which is something we've already talked about. And we know this equation, negative Q lost is equal to Q gained. And I'm just going to introduce some kind of new ideas, although I've already previewed them, I think, with you. That heat flow, we could look at temperature changes, which we did with Q is equal to Sm delta T. And another thing I mentioned to you were phase changes. And this is something we're going to introduce today. This has to do with heat of fusion, delta H sub F US, and heat of vaporization. These are things, heat of fusion is used when you are melting or freezing, because these are phase changes. And heat of vaporization is used when you are boiling or condensing. So we're going to introduce that today. And then remember, we also said heat flow accompanies chemical reactions. And with chemical reactions, we're going to introduce something called delta H of reaction, which this is coming up, not yet today. All right, so moving back, just a quick review. So there are certain things when we deal with temperature changes that we have to look up, like specific heat, or we memorized it for water. And so, we can do problems like 10 grams of water changes, I'll use that delta, temperature from, say, 20 degrees Celsius to 30 degrees Celsius. And we can, ask ourselves, well, what is Q? And we can plug in our numbers. We know specific heat of water, we know the mass of the water, and we know final minus initial temperature, and we can find Q. So we've been doing that already. This is essentially a plug and chug kind of a problem, right? You have a formula, you got to figure out what you need to put in, and you put it in. What we're going to now focus on, because that's old, today are phase changes. And phase changes, when this happens, there's no temperature change at the point that the phase change is occurring. So I'm going to show you an example of this. I'm going to actually show you two different examples. And the heat of fusion and the heat of vaporization are actually numbers, and we would look them up. So you don't have to memorize them. So I'm going to do two different problems. One problem, I'm going to deal with the phase change of melting. And the other one, I'm going to use the phase change of condensing. Just to kind of make the point of how we incorporate this. So melting. As soon as I see melting, I know that I need to somehow look up a heat of fusion for a substance. So I'm going to say I looked up a heat of fusion for the substance I'm going to write this problem about. And I look it up, and it says 10 kilojoules per mole on the table I look it up at. And so here's my problem. 10 grams of solid melts. And the molar mass of the solid, make it easy, is 100 grams per mole. And I want to know, what is Q, essentially? Now, here's the one thing that you need to know about heats of fusion and heats of vaporization. They need the sign added, plus or minus. So it has to go back with, remember, if it's energy's going out, then it's negative. If energy's going in, then it's positive. So what we need to think about is, if something is melting, is heat going into it, or is heat going out of it, or energy, right? Well, to melt something, you have to put energy in, and energy in is positive. That means our heat of fusion that we are going to use is positive 10 kilojoules per mole. I simply added this. This had no sign attached to it. Here's the difference. This, instead of doing plug and chug, I would do as unit analysis. So if I'm going to try to answer the question, this is a great conversion. Helps me convert between kilojoules and moles or moles and kilojoules. Well, I have 10 grams. I don't have kilojoules or moles, but I could turn that into moles. So if I have 10 grams of a solid, and I know the molar mass, 100 grams per mole, then I can use this as a conversion. And I'll put mole on the bottom so it cancels. Kilojoules on the top, it's 10 kilojoules per mole. And everything cancels except kilojoules. And I get, whoops, that didn't right, there we go. Maybe, oh, stuff is just, there we go. 1 kilojoule. So that would be the amount of energy required to melt that solid. If I did a problem with condensing, let's say that I'm condensing, by the way, I use a heat of vaporization. So let's say for this problem, the heat of vaporization that I look up for the substance I'm going to give you a problem is 50 kilojoules per mole. Remember, that has no sign attached to it. So here's the problem. 10 grams of a liquid condenses. And it's going to be the molar mass. We'll keep it at 100 grams per mole. And I want to know, what is Q? Same idea here, you guys. But I have to think about, is energy going in or is energy going out? Well, if it condenses, boiling, I have to put energy in. Condensing, it has to get rid of energy. So this one is energy out. And energy out means it's a negative value. So my heat of vaporization, I'm going to add a negative sign to my 50 kilojoules per mole. Great. This helps me convert between kilojoules and moles. I have grams, so I'm going to try to get that into moles. So just like before, 10 grams of my solid at 100 grams per mole. And now I can use this, negative 50 kilojoules per mole. Mole goes on the bottom, so it cancels. Negative 50 kilojoules. And when I get that, I get a negative 5 kilojoules. That's the amount of energy that is lost to condense that. So we're not going to deal with heat of reaction because that's coming up later, but very shortly. But I want to show you how that fits into what we've been doing. So I'm going to show you something known as a heating curve. And with a heating curve is a graph. Since I have a graph and it looks like this. And on this axis, this is temperature, and so this is going to be for water. And this is just versus time, really, as we add heat. And so this is a heating curve for water. So in other words, if I start with water like down here in this region, it's ice. In this region, between 0 and 100, our H2O is a liquid. Above 100, our H2O is steam. So this is solid, this is liquid, and this is a gas. So think about what that means happens here at 0. That's a phase change. So if we're going in this direction, it's melting. If we're going in this direction from liquid to solid, it's freezing. And same with up here. This is also a phase change at 100. Well, at 100, water starts to boil. So as we go from a liquid to a gas in this direction, it boils. If we went the other way from a gas to a liquid, it would condense. Since those are the phase changes, it's in this region here that we would use the heat of fusion when we're in that region. And this phase change, boiling and condensing, this is the time when we would use the heat of vaporization. Any other point, and notice you guys, there's no temperature change in these areas. So we can't use Q equals S on delta T. But in all the other areas, there is. So in this region, we could have ice that's really cold become warmer ice. We could use SM delta T. In this region, we could have cold water become warm water. We could use Q is equal to SM delta T. And once you get steam at 100, you can actually get it hotter than 100, and you could have a temperature change, and you could use Q is equal to SM delta T. The specific heat capacity for water that you memorized is this one, because the specific heat of steam is actually different, and the specific heat of ice is actually different. So this, the specific heat of liquid water, has that 4.184 joules per gram degree Celsius. So here are the heat of fusions. The heat of fusion for water, just so you know, is 6.02 kilojoules per mole. The heat of vaporization for water is 40.6 kilojoules per mole. One of the things I want you to remember is these numbers, you must add the sign. They don't have the sign, so you have to think, is energy going in? Then it's positive. Is energy leaving? Then it's negative. Just so you know, if it's boiling, you're putting energy in. If it's melting, you're putting energy in. They'll be positive. If it's condensing, energy's coming out, it'll be negative. Or if you're freezing, energy's coming out, and it will be negative. So what I'm going to do is 2 example problems, and that will wrap it up. Here's the first example. How much heat is released when 100 grams of steam condenses to liquid water all at 100 degrees Celsius? Okay. Well, if we think about this heating curve that I just drew, and this is 100, we have 100 grams of steam, but it's at 100 degrees, and it's condensing to a liquid at 100 degrees. So here's where it's all steam. Here's where it's all liquid. In the middle, it's in the process of condensing. So both phases of matter exist. So in this area, I have to use my heat of vaporization, which I know is 40 for water, 0.6 kilojoules per mole. Well, is it negative or positive? Well, it's condensing. Heat is released. That's given off. So I am going to add a negative sign to that. It's important you remember to do that. That's my conversion from kilojoules to mole, moles to kilojoules. I have grams. So 100 grams of steam, I'm going to convert that to moles. That's water, right? 18.02 grams in a mole. And negative 40.6 kilojoules per mole. Grams, moles cancel, and what I get is negative 225 kilojoules. So that's the amount of energy released. The negative tells me it's released. Include the negative. All right, last example. How much heat is required to raise the temperature of 20 grams of ice at 0 degrees Celsius to steam at 100 degrees Celsius? There's my little heating curve. It's getting uglier. I'm just putting in my temperatures. I want us to think about where we are, where we've been. So this is saying we have ice, solid, at 0. Well, that's here, because at this point it's liquid. this point, it's all solid. And at this point, it's melting. It's both. So we're starting here. Then we have to heat it all the way up to steam. So apparently we have to melt it. We have to heat the water. And now this is the liquid part. And then we have to get it to steam at 100. So where we're starting is here. Where we're ending is here. This actually shows me I need 3 steps to answer this question. 1, I need to melt it. 2, I need to raise the temperature. 3, I need to boil it. So that's what we're going to go ahead and do. So, number 1, let's find out how much energy it takes to melt the ice. So we're going to use the heat of fusion here. That's the place we use it. It's 6.02 kilojoules per mole. Is it energy in or out to melt it? It's energy in, so it's a positive value. Great. I have 20 grams of ice. I'm going to convert it into moles so I can use it. So 18.02 grams. Eek. Whoa, I don't need that open. In a mole. And then I'm going to use this 6.02 kilojoules positive per mole. What I get is 6.7 kilojoules. That's how much energy it takes to melt the ice. So that's this. Great. Number 2, I have to take that now liquid water from 0 degrees Celsius, and I've got to heat it all the way up to 100 degrees Celsius before it can boil. That is a temperature change. So I'm going to use Q is equal to SM delta T. All right. Q is equal to specific heat of liquid water, 4.184 joules per gram degrees Celsius, times the mass of the water, 20 grams, times my temperature change. Final temperature is 100. Initial temperature was 0. And when I do that, I get, my calculator says 8,368 joules, but I'm only allowed 2 sig figs. So I'm going to make that 8,400 joules. And that's how much energy, and that's positive, how much energy it takes to heat the water. All right. That was this. Now we have one more. We need to figure out how much energy does it take to boil the water. So we're going to go ahead and boil the water. We have that heat of vaporization because it's boiling, and that's 40.6 kilojoules per mole. It takes energy in because it's boiling, so that's a positive number. And now we're going to do the same thing like we did with the melting. 20 grams of water, turn it into moles so we can use this. 18.02 grams in a mole. And then 40.6 kilojoules for every mole to melt it, and I get 45 kilojoules. That's how much energy it takes to boil the water. So if I go back to my original question, how much heat is required to raise it all the way from ice at 0 to steam at 100? I need to add all of those. So I've got 6.7 kilojoules, 8,400 joules. That's not the same unit, so I might want to convert it into kilojoules. And that's 8.4 kilojoules, so that I have the same unit. And I have 45 kilojoules. So my total Q will be the 6.7 kilojoules to melt the ice, plus the 8.4 kilojoules to warm the water, plus the 45 kilojoules to boil the water. And when I add that together, and then I'm rounding to the ones place, I get 60 kilojoules. That's a positive number. Energy in. That's it. We'll see you tomorrow.